13.8 billion years. That number has been carved into every textbook, every documentary, every model of cosmic history. The age of everything, except now, we know it's wrong. The James Webb Space Telescope just revealed galaxies that shouldn't exist, stars older than time itself, and structures so mature they mock our timeline. Scientists are rewriting reality. The universe might be 26.7 billion years old, twice what we thought, and what existed before the Big Bang. Something cold, empty, and stranger than you can imagine. If you're fascinated by these cosmic revelations, prepare yourselves. We begin. December 2021 changed everything. A telescope the size of a tennis court unfolded in space, 1 million miles from Earth. The James Webb Space Telescope carried mirrors coated in gold, instruments cooled to nearly absolute zero, and the ability to see further back in time than any machine ever built. Scientists expected to peer into the cosmic dawn, that period 500 to 800 million years after the Big Bang, when the first galaxies flickered to life. They expected baby structures, tiny clumps of stars stumbling into existence. What they found instead made veteran astronomers say things like, "It's bananas," and we discovered the impossible. The telescope pointed toward a patch of sky near the Big Dipper. Hubble had looked there before and seen nothing special. But Webb sees in infrared, catching light that has stretched across billions of years of cosmic expansion. Within days of releasing its first deep field images, researchers spotted something wrong. 6 bright red dots appeared in the data. At first glance, they looked like distant quasars or maybe dust. Then the team measured their redshift, that telltale signature of how far light has traveled. The numbers came back impossible. These objects existed just 500 to 700 million years after the universe began. Here's why that shattered everything. According to our models, early galaxies should be small, dwarf systems containing maybe 100 million stars, slowly pulling together under gravity's patient hand. These 6 objects contain tens of billions of stars each. Some appeared nearly as massive as our modern Milky Way, which took over 13 billion years to build. One researcher from the University of Colorado Boulder put it plainly: you just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. The mathematics of galaxy formation are brutal. Stars don't just appear. Gas must cool, collapse under gravity, ignite fusion. That takes time, lots of it. Our Milky Way births maybe 2 new stars per year. For these ancient galaxies to reach their observed size in just 700 million years, they would need to create hundreds of stars annually for hundreds of millions of years straight. Even then, the numbers barely work. Add another problem. The early universe lacked heavy elements. The first stars formed from pure hydrogen and helium. Heavier matter that makes large galaxy formation easier didn't exist yet. These objects somehow bypassed all the rules. More data made things stranger. Some of these early galaxies appeared smaller in size, despite containing more mass than larger neighbors. That's backwards. In cosmic evolution, more mass accumulates in bigger systems over time. These acted like compressed giants, packing Milky Way level mass into structures a fraction of the size. The density seemed impossible. Another team found what they called red monsters, 3 ultra-massive galaxies existing within the first billion years, forming stars with terrifying efficiency. Standard cosmology suggests only 20% of available gas converts into stars. These ancient behemoths appeared to be converting far more, as if the early universe played by different physics. The discovery triggered what scientists call the impossible early galaxy problem. It's not just one weird object. Webb kept finding them. Dozens of massive, mature galaxies existing when the cosmic timeline says they shouldn't. Some showed disk structures and bulges typically associated with billions of years of evolution. Others displayed organized spiral patterns. These weren't chaotic clouds of newborn stars. They looked grown up, established. ancient in appearance despite being cosmically young. Every new observation deepened the mystery. Either our understanding of galaxy formation is completely wrong, or something is fundamentally broken with our timeline. Teams worldwide scrambled to explain it. Maybe black holes in these galaxies' cores produce extra light, making them appear more massive than they are. Recent research suggests this might account for some cases. The light we interpret as starlight could partly be radiation from gas swirling into supermassive black holes. That would reduce the estimated stellar mass. But even cutting the numbers in half leaves galaxies far too large for their age. Another proposal suggests stars formed faster in the early universe because it was denser, making it harder for gas to blow away during star birth. Possible, but the effect would need to be extreme to match observations. What nobody expected was the simplest explanation. What if the galaxies aren't too big? What if the universe is too young? What if our most fundamental assumption about cosmic age is wrong by a factor of 2? The James Webb revelations didn't just show us distant galaxies. They showed us a universe that doesn't fit inside 13.8 billion years. Something has to give. Either the physics of star formation is alien in the early cosmos, or time itself is longer than we thought. But there's more evidence beyond these galaxies, and it gets even stranger from here. For nearly a century, scientists have been trying to answer one question: how old is everything? The number we arrived at, 13.8 billion years, didn't come from a guess. It came from measuring the universe's expansion rate, observing the oldest stars, and analyzing radiation left over from the Big Bang itself. This age became cosmology's bedrock. It appears in every textbook. Every model of cosmic evolution builds from it. But the path to this number was messier than most people realize, and the cracks in its foundation have been there from the start. The story begins in the 1920s with Edwin Hubble. Using the most powerful telescope of his era, Hubble measured the light from distant galaxies. He noticed something shocking. The light was redshifted, stretched toward longer wavelengths. The farther the galaxy, the more its light shifted. This wasn't random. It followed a pattern. More distant galaxies moved away faster. Their light stretched more by the expansion of space itself. Hubble realized the universe wasn't static. It was growing, and if you run that expansion backward in time, everything must have been together at a single point. That point became known as the Big Bang. But knowing the universe is expanding doesn't immediately tell you its age. You need to measure how fast it's expanding. That rate is called the Hubble constant, and measuring it turned into one of astronomy's biggest headaches. Early estimates varied wildly. When the Hubble Space Telescope launched in the 1990s, scientists thought the universe might be anywhere from 7 billion to 20 billion years old. That's a range bigger than the age of Earth. The uncertainty came from the difficulty of measuring cosmic distances accurately. A small error in distance translates to a huge error in age. By the early 2000s, new techniques and better telescopes narrowed the range. Scientists used observations of Type 1a supernovae, exploding stars that shine with consistent brightness. By measuring how dim these supernovae appeared, astronomers calculated their distance. Combining thousands of measurements across cosmic history, they refined the expansion rate. Another breakthrough came from studying the cosmic microwave background, that faint radiation left over from when the universe was only 380,000 years old. The European Planck satellite mapped this radiation with incredible precision, revealing tiny temperature fluctuations that encode information about the universe's age, composition, and fate. All the methods converged on the same answer: 13.797 billion years, give or take 23 million years. That's an uncertainty of less than 1%. It seemed like cosmology had finally nailed down its most important number. The Lambda CDM model, our standard picture of cosmic evolution, incorporated this age. It explained how matter clumped into galaxies, how the cosmic microwave background formed, how light elements were created in the Big Bang's first minutes. Everything fit together into an elegant story. The universe began in a hot, dense state. It expanded and cooled. Stars formed, galaxies grew, and here we are, 13.8 billion years later. But even as this consensus formed, troubling observations accumulated. Some measurements of the Hubble constant using nearby galaxies suggested a faster expansion rate than the cosmic microwave background predicted. A faster expansion means less time has passed, implying a younger universe. Some estimates dropped the age to as low as 11.4 billion years. Others pushed it to 12.7 billion. This became known as the Hubble tension, a growing disagreement between different measurement methods that refuses to go away. It's not an error, it's a real discrepancy that suggests something in our model is incomplete. Then there are the stars. Globular clusters in our own Milky Way galaxy contain some of the oldest stars in existence. These clusters formed early, before the galaxy fully took shape. By studying the brightness, temperature, and chemical composition of their stars, astronomers can estimate ages. Most cluster stars come out to around 12 to 13 billion years old. Reasonable, given the universe's age, but a few stars push the limits uncomfortably. They appear to be as old or older than the universe they inhabit. That should be impossible. An object can't exist before the container that holds it. The most famous case is a star called Methuselah, catalogued as HD 14283, located just 200 light-years away. Close enough to study in detail, this star presented a mathematical nightmare. Its low metal content indicates extreme age. Metals, in astronomy terms, means any element heavier than hydrogen and helium. The early universe had almost no metals. They had to be created inside stars and scattered by supernovae. Low metal stars formed early, before much metal existed. Methuselah's metal content is 1/250th that of our solar system. Ancient doesn't begin to cover it. Measurements of Methuselah's age kept coming back wrong. Early estimates placed it at 16 billion years old. Later refinements using Hubble Space Telescope data reduced that to 14.5 billion years, plus or minus 800 million years. Even with the uncertainty, the star's most likely age exceeded the universe's calculated age. Astronomers reassured the public that the error bars overlapped, so technically there was no contradiction. But the fact that the central estimate kept coming back older than cosmic time bothered everyone. More recent models have adjusted the star's age downward to somewhere between 12 and 14 billion years. The paradox seemed resolved, except it really wasn't. It just got hidden in uncertainty ranges. These weren't isolated problems. They were symptoms of something deeper. The 13.8 billion year age worked mathematically. It satisfied the equations of general relativity and matched most observations of the cosmic microwave background. But it required the universe to be incredibly efficient at forming structures. Galaxies had to assemble fast. Stars had to ignite early. Everything needed to happen on a tight schedule. When James Webb looked back and found mature galaxies and massive structures already in place at cosmic dawn, the schedule broke. There wasn't enough time. The universe was operating ahead of the timeline we gave it, perhaps because the timeline itself was wrong. The deeper James Webb looked into the cosmic past, the more impossible the universe became. After the initial 6 massive galaxies shocked astronomers, the telescope kept finding more. Dozens of bright, red, mature structures existing in the first billion years. Some appeared as mere blobs of light, but their properties revealed ages and masses that defied explanation. These weren't anomalies, they were everywhere. The early universe was packed with fully developed galaxies that standard cosmology said should be tiny, blue, baby systems, just beginning their lives. One team analyzing Webb data from the Cosmic Evolution Early Release Science Survey catalogued over 250 young galaxies existing between 800 million and 1.5 billion years after the Big Bang. Most were turbulent, clumpy systems, which matched expectations. But a significant fraction showed organized structures, rotating disks, central bulges. Features that take billions of years to develop through gravitational interactions and mergers. Finding one or two precocious galaxies could be explained as statistical flukes. Finding hundreds suggested a systematic problem with the models. The numbers didn't just barely exceed predictions, they obliterated them. Standard theory suggests that matter in the early universe clumped together slowly. Dark matter halos formed first, invisible scaffolds of gravity. Regular matter fell into these halos, cooled, and eventually condensed into stars. The process was gradual. Small structures merged into larger ones over billions of years. Our Milky Way formed through countless mergers of smaller galaxies. Its spiral shape and organized disk structure took 10 billion years to develop. Webb was showing galaxies with similar features existing when the universe was less than 1 billion years old. They had 1/10 the time, but looked just as mature. One particularly troubling discovery involved 3 galaxies nicknamed the Red Monsters, found by an international team led by researchers at the University of Geneva. These systems existed within the first billion years, but appeared nearly as massive as our modern Milky Way. Each contained hundreds of billions of stars. The lead researcher stated plainly, "Our findings are reshaping our understanding of galaxy formation in the early universe." The red monsters weren't just big. They were incredibly efficient at star formation. Models suggest only 20% of available gas converts into stars in typical galaxies. These ancient systems converted far more, possibly up to 50% or higher. That efficiency shouldn't be possible. Star formation is messy and wasteful. When gas collapses to form stars, the newborn stars blast radiation and stellar winds into surrounding material, heating it and blowing much of it away before it can form more stars. This self-regulation limits how fast galaxies grow. Young galaxies especially should be inefficient because their first massive stars exploded as supernovae quickly, violently disrupting further star formation. The red monsters somehow bypassed this. They grew at rates that seemed to violate the physics of feedback processes. Either the early universe played by different rules, or these galaxies are older than we think, giving them more time to accumulate their mass. Another puzzle involves the galaxies' sizes. Some of Webb's discoveries pack enormous stellar masses into surprisingly compact volumes. They appear smaller than expected given their mass. One might think this just means they're dense, but the density creates its own problems. Gravity in such concentrated systems should have triggered rapid bursts of star formation and black hole growth. The galaxies should have burned through their gas supplies quickly and shut down. Instead, they appear to be thriving, actively forming stars, showing no signs of the quenching process that stops star formation in dense environments. It's as if the physics of gravity operates differently in the early universe. Teams proposed dozens of explanations. Maybe the initial mass function, the distribution of star sizes when they form, was different in early galaxies. If the first galaxies produced more massive stars than modern ones, those stars would have been brighter, making the galaxies appear more massive than they actually were. But massive stars die quickly. Within a few million years, they explode. The galaxies Webb observed existed for hundreds of millions of years. The massive star population would have turned over many times. The brightness should have faded. It didn't. Another idea suggested that supermassive black holes at the galaxy's centers contributed significant light. Gas spiraling into the black holes would shine brightly, adding to the total luminosity. Recent observations support this, in some cases, but not all. Many of the massive early galaxies show no signs of active black hole feeding. The simplest explanation remained the most unsettling. These galaxies aren't too big for their ages. They're exactly the right size for the amount of time they've actually existed. But that time isn't 700 million years. It's much longer. If the universe is twice as old as we think, these galaxies had over 1 billion years to form instead of half that. Suddenly, the impossible becomes merely difficult. The timeline pressure eases. Star formation rates don't need to be absurdly high. Efficiency doesn't need to violate physics. The galaxies just had more time. This realization spread through the astronomical community like a slow wildfire. Papers began hedging their language. Instead of declaring the galaxies impossible, researchers described them as challenging or unexpected. The shift was subtle but significant. Scientists were entertaining the possibility that the James Webb discoveries weren't revealing exotic early universe physics. They were revealing that our cosmic clock was miscalibrated. Every observation that seemed to break the rules suddenly made sense if you doubled the available time. The universe wasn't breaking physics. It was breaking our assumptions about its age. And if those assumptions were wrong, then everything built on them needed to be reconsidered, including what we think happened at the very beginning. 200 light-years from Earth, in the constellation Libra, floats a star that shouldn't exist, catalogued as HD 14283. Astronomers call it Methuselah, after the biblical figure who supposedly lived 969 years. But this star's age makes even that ancient patriarch look like an infant. Depending on which measurements you trust, Methuselah is somewhere between 12 and 14.5 billion years old. The universe, according to our best calculations, is 13.8 billion years old. Do the math. The paradox screams at you. How can a star be older than the universe that contains it? Astronomers have known about this star for over a century. It races across the sky at 800,000 miles per hour, a high-velocity star moving through our galactic neighborhood. Its speed and trajectory suggest it formed elsewhere and was flung into our region, possibly when a dwarf galaxy was torn apart by the Milky Way's gravity billions of years ago. But the star's true significance became clear when spectroscopic analysis revealed its chemical composition. Methuselah contains barely any elements heavier than hydrogen and helium. Its metallicity is 1/250th that of our solar system. This isn't just old. This is primordial. The early universe produced only hydrogen, helium, and trace amounts of lithium in the Big Bang's first minutes. Everything else, every atom of carbon, oxygen, iron, gold, had to be forged inside stars and scattered by supernovae. The first generation of stars, called Population 3 stars, formed from pure primordial gas with essentially zero metals. They lived fast, died young in spectacular explosions, and seeded space with heavier elements. The second generation, Population 2 stars, formed from gas enriched by those first supernovae. They have low metallicity but not zero. Methuselah is a Population 2 star. It formed after the first stars died, but before much metal accumulated. That places its birth extremely early in cosmic history. Measuring a star's age requires understanding its internal physics. Stars spend most of their lives on what astronomers call the main sequence, burning hydrogen into helium in their cores. Eventually, the hydrogen runs out. The core contracts and heats up. The outer layers expand. The star becomes a red giant. How long this takes depends on the star's mass, its initial composition, and details of how heat and elements move through its interior. Methuselah has already left the main sequence. It's a subgiant, just beginning its expansion toward the red giant phase. By measuring its current brightness, temperature, and chemical composition, then modeling its evolution backward, astronomers can estimate when it formed. The first serious age estimate came from observations with the Hipparcos satellite in 2000. The result was shocking: 16 billion years old. That's older than any reasonable estimate of the universe's age. It created an instant crisis. Either the star's age was wrong, or the universe's age was wrong, or our understanding of stellar evolution was fundamentally broken. Scientists scrambled to refine the measurements. In 2013, The Hubble Space Telescope's fine guidance sensors measured Methuselah's distance with 5 times better precision than Hipparcos. Better distance measurement leads to better estimates of the star's true brightness, which affects the age calculation. The new result: 14.5 billion years, plus or minus 800 million years. That uncertainty range became crucial. The lower bound of the estimate, 13.7 billion years, technically overlapped with the universe's age. Scientists emphasized this overlap, arguing there was no real paradox. Within the error bars, everything was consistent, but privately, many felt uncomfortable. The central estimate, the most likely age, still exceeded cosmic time, and there was something suspicious about how the error bars kept getting adjusted to barely include the universe's age. It felt like forcing a solution rather than finding one. More recent studies in 2021 and 2022 revised the age again, this time using interferometric observations and more sophisticated stellar models. The new estimates ranged from 12 to 14 billion years, depending on assumed parameters. But Methuselah isn't alone. Other ancient stars in globular clusters show similar age tensions. Some estimates exceed 13 billion years. Others push right up against the cosmic age limit. The Methuselah star just happens to be closest and best studied, making it the poster child for the problem. These ancient stars all share low metallicity, indicating formation in the early universe. They all show evolved states, having already burned through most of their hydrogen fuel. And they all present age estimates that make cosmologists nervous. The more accurately we measure their properties, the older they seem to get. Some researchers argue the problem lies in stellar physics. Maybe we don't fully understand how elements diffuse through a star's interior. Maybe magnetic fields or rotation affects evolution in ways the models don't capture. These factors could make stars appear older than they actually are. Others point to uncertainties in measuring distances and brightness. A small error in distance produces a large error in age. Perhaps Methuselah is closer than we think, making it dimmer and younger than current estimates suggest. These explanations work on paper. They allow scientists to maintain that the universe's age is correct and the star ages just need better refinement. But there's another possibility nobody wanted to seriously consider until recently. What if Methuselah's age is roughly correct? What if the star really is 14 billion years old or more? That doesn't mean the star is older than the universe. It means the universe is older than 13.8 billion years, much older. If the universe is actually 26 billion years old, Methuselah stops being a paradox. It becomes just another ancient star with a reasonable age. The timeline expands enough to comfortably fit these stellar patriarchs without mathematical gymnastics or error bar manipulation. And suddenly, the age tension disappears not because we fixed the star measurements, but because we fixed the clock itself. In July 2023, a physicist at the University of Ottawa published a paper that could rewrite cosmology. Rajendra Gupta, an adjunct professor, proposed something radical. The universe isn't 13.8 billion years old, it's 26.7 billion years old, nearly double the accepted age. His model didn't come from random speculation. It came from trying to solve multiple problems in modern cosmology that have bothered scientists for years. The impossible early galaxies, the stars older than time, the tension in measurements of cosmic expansion. Gupta showed that all these problems disappear if you just let the universe be twice as old. The core of Gupta's work combines two ideas that mainstream cosmology had abandoned. The first is tired light theory, proposed in 1929 by Swiss astronomer Fritz Zwicky. Zwicky suggested that photons lose energy as they travel vast cosmic distances. Light gets tired. This energy loss would cause redshift, the stretching of light toward longer wavelengths, without requiring space itself to expand. For decades, this theory competed with the Big Bang expansion model. But observations of supernovae and the cosmic microwave background didn't match tired light predictions. The theory was rejected. Zwicky's idea became a historical footnote, mentioned only to show what doesn't work. Gupta brought tired light back from the dead, but with a twist. Instead of using it alone, he combined it with the standard expanding universe model. In his framework, redshift is a hybrid phenomenon. Part of the redshift comes from cosmic expansion, as the Big Bang model says. Part comes from photons losing energy over time, as Zwicky suggested. This dual mechanism changes how we interpret the light from distant galaxies. Objects we thought were extremely far away and extremely young might actually be somewhat closer and older. The tired light component makes their light appear more redshifted than expansion alone would cause. Suddenly, the early universe isn't as young as we calculated. The second idea Gupta incorporated comes from Paul Dirac, one of the founders of quantum mechanics. In 1937, Dirac proposed that fundamental constants of nature might not be constant. These coupling constants determine how particles interact. They set the strength of forces. If these constants changed over cosmic history, the physics of the early universe would differ from today's physics. Gupta specifically considered evolving coupling constants related to light and particle interactions. By allowing these constants to vary over time, he could extend the timeline of galaxy formation without violating current observations. When Gupta combined tired light with evolving coupling constants and ran the mathematics through observations of supernovae and cosmic microwave background data, something remarkable happened. The model fit. Not perfectly, but well enough to be taken seriously. More importantly, it solved problems. The impossible early galaxies from James Webb stopped being impossible. Given 26.7 billion years instead of 13.8, those galaxies had over 1 billion years to form their stars and build their masses. The timeline pressure vanished. Star formation rates could be normal. Efficiency didn't need to be absurdly high. The galaxies just had more time. The Methuselah star paradox also resolved itself. A 14 billion-year-old star isn't older than a 26.7 billion-year-old universe. It's just an ancient star that formed in the early epochs, 5 or 6 billion years after the actual beginning. The uncomfortable error bar overlaps disappeared. The age tension between different measurement methods eased. Gupta's model stretched cosmic history long enough to comfortably accommodate all the troublesome observations that didn't quite fit the 13.8 billion year framework. It was elegant in its simplicity. One change, doubling the age, fixed multiple problems at once. The scientific community's reaction was mixed. Some researchers found the work intriguing and worth further investigation. The paper was published in monthly notices of the Royal Astronomical Society, a respected journal. Other scientists criticized it sharply. They pointed out that Gupta's model only considered supernova data, not the full range of cosmological observations. A comprehensive cosmological model must explain galaxy distributions, gravitational lensing, the detailed structure of the cosmic microwave background, and measurements of universal expansion at different epochs. Critics argued that tired light, even in hybrid form, couldn't satisfy all these constraints. The evolving coupling constants idea, while interesting, lacked independent evidence. However, dismissing Gupta's work became harder when independent lines of evidence started supporting an older universe. In 2024, researchers analyzing globular clusters using a different method found evidence suggesting the universe could indeed be older than standard models indicate. They developed a more objective technique for determining cluster ages based on blue straggler stars, unusual objects that appear younger than their neighbors. This method yielded ages consistent with a universe significantly older than 13.8 billion years. The convergence of evidence from multiple independent approaches made the possibility impossible to ignore. Gupta himself has been careful in presenting his findings. He doesn't claim absolute certainty. He describes his model as addressing specific problems in current cosmology and offering a potential resolution worth serious consideration. In interviews, he emphasized that science advances through testing alternative ideas. The Lambda CDM standard model works well for many observations but struggles with the James Webb discoveries and ancient star ages. Rather than forcing those observations to fit the model, perhaps the model needs revision. Doubling the universe's age is admittedly radical, but so was the Big Bang itself when first proposed. Revolutionary ideas often seem absurd until evidence forces acceptance. The implications extend beyond just fixing technical problems. If the universe is 26.7 billion years old, the entire story of cosmic evolution changes. The gap between the Big Bang and the first stars lengthens. Early galaxies had more time to grow and merge. The Milky Way's formation history gets rewritten with a longer, more complex timeline. Life on Earth, appearing around 4 billion years ago, occupies an even tinier fraction of cosmic history, and the question of what happened before the Big Bang becomes even more pressing, because now there's more time to account for, more history to explain, and more mystery about what conditions preceded the explosion that started everything we see. In 1929, while Edwin Hubble was discovering the expanding universe, Fritz Zwicky was thinking about light differently. A Swiss astronomer working in California, Zwicky noticed the same galactic redshifts Hubble observed. But where Hubble saw expanding space stretching light to longer wavelengths, Zwicky saw something else. What if light simply got tired? Photons travel for billions of years across the void. Maybe they lose energy along the way, gradually shifting toward the red end of the spectrum without any space expansion at all. Zwicky called it tired light theory, and for a while, it competed seriously with the Big Bang model. The idea has intuitive appeal. Energy doesn't come from nowhere. Light crossing cosmic distances might interact with something in the vastness between galaxies. Maybe encounters with intergalactic gas particles or gravitational interactions with matter sap photon energy bit by bit. Each interaction would be tiny, unnoticeable, over short distances. But after billions of light years, the cumulative effect could produce the redshift we observe. Zwicky's model offered an alternative to space expansion. The universe could be static, eternal, unchanging. Galaxies weren't flying apart. Their light was just losing energy as it traveled to our telescopes. For decades, tired light remained viable. Einstein initially favored a static universe and found tired light conceptually appealing. Some astronomers preferred it to the bizarre implications of the Big Bang, which seemed almost religious in suggesting a moment of creation. But observations gradually killed the theory. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background, faint radiation left over from when the universe was 380,000 years old. This afterglow of the Big Bang had exactly the properties predicted by expansion models. Tired light couldn't explain it. The final nail came from observations of distant supernovae in the 1990s. Type 1a supernovae explode with consistent brightness, making them excellent distance markers. Astronomers noticed that light from distant supernovae appeared not just redder, but also stretched in time. Explosions that should take weeks appeared to last months when viewed from extreme distances. This time, dilation effect is predicted by expanding space. If space expands while light travels to us, the light waves stretch, and timestamps on those waves spread out. Tired light predicts no time dilation because photons just lose energy without temporal effects. The supernova observations matched expansion predictions perfectly. Tired light was declared dead. Cosmology textbooks relegated it to the historical curiosities section. Yet Zwicky's core insight, that photons might lose energy through mechanisms beyond space expansion, never completely disappeared. A few researchers continued exploring variations. What if tired light wasn't wrong but incomplete? What if both expansion and energy loss occur? Gupta's breakthrough in 2023 was recognizing that a hybrid model could work. By allowing redshift to have two components, one from expansion and one from tired light effects, he could reinterpret observations in a way that extended cosmic timelines without contradicting key data. The mathematics works like this. Standard cosmology interprets all redshift as expansion. A galaxy with redshift factor of 6 existed when the universe was 1/7 its current size. That places it very early and very far away. But if half the redshift comes from tired light, the galaxy isn't as distant or as early. It's somewhat closer and older. The effect compounds over cosmic distances. For nearby objects, the difference is negligible. For the most distant objects visible to James Webb, the difference becomes enormous. Galaxies we thought formed 500 million years after the Big Bang might have actually formed 1 billion or even 2 billion years later. The extra time solves the maturity problem. Critics immediately attacked the hybrid model. They pointed out that tired light predicts different surface brightness patterns for galaxies than expanding space does. Observations favor expansion. They noted that the cosmic microwave background's uniformity and spectrum are explained beautifully by expansion, but not by tired light mechanisms. These aren't minor issues. They're fundamental tests that originally killed the theory. Gupta's response was that his model isn't pure tired light. It's a small tired light contribution combined with expansion. The expansion component handles most observations normally. The tired light component just adds a correction that changes distance and age interpretations. Whether this works depends on detailed calculations and future observations. Some researchers who initially dismissed Gupta's paper started reconsidering after James Webb continued finding problematic galaxies. If the alternative is accepting that early universe physics was radically different, maybe reconsidering tired light isn't so crazy. Science has a history of resurrecting old ideas when new data demands it. Continental drift was mocked for decades before becoming plate tectonics, the foundation of geology. Atoms were once considered absurd. Black holes seemed like mathematical fantasies. Tired light might be following a similar arc from rejected theory to useful component of a better model. The deeper question is what physically causes tired light effects if they exist. Zwicky never provided a satisfying mechanism. Photons don't just lose energy spontaneously. Something must cause it. Modern proposals involve interactions with quantum vacuum fluctuations, the seething activity of particle pairs appearing and vanishing in empty space. Perhaps photons exchange tiny amounts of energy with these fluctuations over cosmic distances. Another idea involves gravitational interactions with the cosmic web, the large-scale structure of dark matter and galaxies. As light passes through varying gravitational fields, it might lose energy through mechanisms not fully captured by general relativity. None of these mechanisms are proven. They're speculative attempts to make tired light physically plausible. But that's how science progresses. Observations come first. Phenomena are recognized before mechanisms are understood. We observed cosmic expansion decades before understanding dark energy. We detected gravitational waves a century after Einstein predicted them. If tired light effects are real, the mechanism will eventually be found. The key right now is determining whether observations genuinely require a tired light component or whether they can be explained through conventional physics with a 13.8 billion year timeline. James Webb's ongoing observations will help decide. Every new impossible galaxy tips the scales a bit further toward needing a longer cosmic history. They called them red monsters, for good reason. 3 galaxies, each glowing deep crimson in James Webb's infrared images, each containing nearly as many stars as our entire Milky Way. They existed less than 1 billion years after the Big Bang, during the epoch astronomers call cosmic dawn. According to everything we know about galaxy formation, they shouldn't be there. Their existence challenges not just our timeline, but the fundamental physics of how stars and galaxies come into being. These aren't minor anomalies. They're cosmic behemoths that appeared when the universe was supposedly still in its infancy. The discovery came from an international team using Webb's FRESCO program, which leverages the near-infrared camera's GRISM spectrograph to measure precise distances and properties of early galaxies. The team, led by researchers at the University of Geneva, systematically studied galaxies in the first billion years, looking for patterns in their formation. What they found was unexpected. Most early galaxies behaved as predicted: small, turbulent, inefficient at forming stars. But 3 objects stood out, massive beyond anything models predicted, dense, mature-looking, and terrifyingly efficient at converting gas into stars. Standard galaxy formation theory is built around dark matter. Invisible matter that doesn't emit light but exerts gravity forms vast halos throughout the universe. Regular matter, the atoms we're made of, falls into these dark matter wells. The gas accumulates, cools, and eventually collapses to form stars. But this process is wasteful. Only about 20% of available gas becomes stars in typical galaxies. The rest gets heated by stellar radiation, blown away by supernova explosions, or locked up in other forms. This inefficiency limits how fast galaxies can grow. It's a fundamental constraint on cosmic structure formation. The red monsters don't play by these rules. Analysis of their stellar masses and star formation rates suggests they converted 40 to 60% of their gas into stars. That's 3 times more efficient than modern galaxies. The lead researcher stated plainly that this efficiency reshapes our understanding of galaxy formation in the early universe. It's not just surprising, it's physically difficult to explain. What mechanism allows early galaxies to avoid the feedback processes that limit star formation? How do they prevent supernovae from blowing away their gas supplies? Why don't stellar winds heat the gas to temperatures where it can't collapse? One possibility involves the density of the early universe. Space was more compressed back then. Matter was packed more tightly. Perhaps in such conditions, gravity overwhelmed feedback effects. Gas couldn't escape even when heated because the gravitational pull was too strong. Stars formed faster because collapse happened quicker in the denser environment. This would explain high efficiency but creates another problem. High density should also trigger rapid black hole growth. The red monsters should have massive black holes at their centers, and those black holes should produce bright quasar emission. Some do show signs of active black holes, but not all. The explanation is incomplete. Another idea suggests the initial mass function was different in early galaxies. The initial mass function describes the distribution of stellar masses when stars form. In nearby galaxies, most stars are low mass, around half the mass of our solar system or less. Massive stars are rare. If early galaxies produced more massive stars, they would look brighter and more massive than they actually are. Massive stars are short-lived, exploding within a few million years. But during their brief lives, they shine intensely. A galaxy filled with massive stars could appear to contain more stellar mass than it really does. The red monsters might be optical illusions created by unusual star formation. Testing this requires observing the galaxies at multiple wavelengths and looking for signatures of massive star populations. Webb's instruments can do this, but the analysis takes time and careful work. Early results are mixed. Some of the massive early galaxies show spectral features consistent with normal stellar populations, not top-heavy ones. Others display unusual emission lines that could indicate massive stars or could indicate something else entirely. The jury is still out. What's clear is that invoking unusual stellar populations alone doesn't fully solve the problem. Even adjusting for this, the galaxies are too large, too early. The simplest solution remains extending the timeline. If the universe is 26.7 billion years old, instead of 13.8, cosmic dawn lasted longer. The first billion years becomes nearly 2 billion years. Galaxies have twice as much time to accumulate mass, form stars, and grow into red monsters. Efficiency doesn't need to be extreme. Stellar populations don't need to be exotic. The physics can be normal. The galaxies just had more time. This explanation bothers some astronomers because it requires rethinking everything built on the 13.8 billion year age. But it has a virtue that complex models lack: simplicity. As Webb continues observing, more red monsters keep appearing. The original 3 aren't unique. They're part of a population of massive early galaxies scattered throughout cosmic dawn. Each new discovery strengthens the case that something fundamental is wrong with our timeline. Either the early universe was a wildly different place with alien physics, or it wasn't as early as we think. The red monsters aren't breaking the laws of physics. They're breaking our assumptions about when those laws were operating. And with each new observation, the possibility that we've miscalculated the age of everything grows stronger. In 1937, physicist Paul Dirac published a paper that most of his colleagues thought was bizarre. Dirac, one of the founders of quantum mechanics and predictor of antimatter, had been thinking about the fundamental constants of nature. These numbers, like the speed of light and the strength of gravity, appear in every equation describing reality. They determine how particles interact, how forces operate, how the universe behaves. Scientists had always assumed these constants were truly constant, unchanging throughout space and time. Dirac asked a simple question: what if they're not? His reasoning came from noticing strange numerical coincidences. The ratio between electromagnetic force strength and gravitational force strength is enormous, around 10 to the 40th power. The age of the universe expressed in atomic time units gives a similar huge number. Dirac found these coincidences suspicious. Maybe they weren't coincidences. Maybe the constants of nature evolve as the universe ages. Specifically, he proposed that the gravitational constant might have been stronger in the early universe and gradually weakened over time. If true, this would mean the physics of the early cosmos operated differently than physics today. The idea was mostly ignored for decades. It seemed untestable. How do you check if constants changed billions of years ago? But modern cosmology has given us ways to look back in time. Light from distant galaxies shows us the universe as it was billions of years ago. By studying the spectral lines in that ancient light, we can measure what the constants were when the light was emitted. Several research groups have done exactly this, looking for evidence that the fine structure constant, which governs electromagnetic interactions, might have varied over cosmic history. Results are tantalizing but not conclusive. Some studies claim to detect tiny variations in the fine structure constant at high redshift, suggesting the constant was slightly different billions of years ago. Other studies find no significant change. The measurements are at the edge of what current instruments can detect. Error bars are large. The scientific community remains divided on whether variations have been proven, but the possibility remains open. If constants do evolve, even slightly, it would transform our understanding of physics and cosmology. Gupta's model incorporates evolving coupling constants as a core component. He doesn't just use Dirac's gravitational constant idea. He considers constants related to how light and matter interact. If these coupling constants were different in the early universe, photons would behave differently. The rate at which atoms absorb and emit light would change. This affects how we interpret observations of distant galaxies. Light we receive from the early universe might carry signatures of different physics, and we've been misinterpreting those signatures by assuming constants never change. The mathematics involved gets technical fast. Coupling constants appear in the equations describing particle interactions. Change the constant, and interaction rates change. This affects stellar evolution, nuclear fusion rates, even the formation of atoms in the early universe. Small changes to constants can have cascading effects through all of physics. Gupta showed that by allowing specific constants to evolve according to particular mathematical functions, he could extend the timeline of cosmic history while still matching observations of the cosmic microwave background and galaxy distributions. Critics point out that evolving constants create their own problems. If the strength of electromagnetic force changed over time, the fusion reactions in stars would have operated differently in the past. This would affect the abundance of light elements produced in the Big Bang and in early stars. We measure those abundances in ancient gas clouds, and they match predictions assuming constant constants very well. Changing the constants to solve one problem risks creating mismatches in element abundances. Gupta's model needs to carefully tune how constants evolve to avoid these issues. Another concern involves fundamental physics theories. Constants aren't arbitrary numbers. They emerge from the underlying structure of quantum field theory and general relativity. Changing them requires understanding why they change and what mechanism drives the evolution. String theory, one approach to unifying physics, predicts that constants could indeed vary if extra dimensions of space change size over cosmic time. But string theory remains unproven and controversial. Basing a cosmological model on speculative physics makes many scientists uncomfortable. Yet the coupling constants idea has a crucial advantage. It provides a physical mechanism for why the universe could be older than standard models suggest. It's not just saying the universe is older. It's explaining how that extra time is consistent with observations that seem to constrain the age. By allowing physics itself to evolve, the model creates wiggle room in the timeline. Processes that we think took a certain amount of time based on today's physics might have taken longer when constants were different. Galaxy formation, star evolution, element creation, all could have operated on extended timescales in the early universe. Testing this requires observations that are just becoming possible. James Webb can study galaxies at extreme distances with unprecedented detail. By measuring the spectra of early galaxies precisely, astronomers can look for anomalies that might indicate different coupling constants. If the fine structure constant was different, spectral lines would appear shifted in specific ways compared to predictions. If stellar evolution constants varied, stars in early galaxies would have different colors and lifetimes than models predict. The data is starting to come in. So far, no smoking gun has appeared, but the search continues, because if constants do evolve, it would be one of the biggest discoveries in physics, with profound implications for how we understand time, space, and the universe's true age. Every astronomer knows the story. In the 1920s, Edwin Hubble pointed telescopes at distant galaxies and measured their light. He noticed something strange. The spectral lines, those distinctive fingerprints created by elements absorbing or emitting specific wavelengths, were shifted toward the red end of the spectrum. The more distant the galaxy, the more extreme the shift. Hubble realized this meant the universe was expanding. Space itself stretched as it grew, pulling galaxies apart and stretching the light traveling between them. Redshift became the foundation for measuring cosmic distances and calculating the universe's age. The concept is straightforward. Imagine drawing dots on a balloon, then inflating it. The dots move apart as the rubber stretches. Light waves behave the same way in expanding space. A photon, emitted from a distant galaxy, travels through space for billions of years. During that journey, space expands, stretching the photon's wavelength. By the time it reaches our telescopes, the light has shifted to longer, redder wavelengths. The amount of shift tells us how much space expanded during the photon's journey, which tells us the galaxy's distance and how long ago the light was emitted. Astronomers express redshift as a number called z. A galaxy with redshift, z equals 1, has doubled its distance from us since emitting its light. The light's wavelength also doubled, shifting from blue toward infrared. Higher redshift means greater distance and earlier cosmic time. James Webb spots galaxies with redshifts around 10 or higher. These objects existed when the universe was just a few % of its current age, or so we thought. The conversion from redshift to age depends critically on knowing how fast space expanded at different epochs. Change the expansion history, and you change what redshift means. Standard cosmology assumes space has been expanding continuously since the Big Bang. The rate of expansion changed over time. Initially, matter and radiation slowed the expansion through gravity. Recently, dark energy started accelerating it, but at any given moment in cosmic history, the expansion rate was determined by the balance of matter, radiation, and dark energy densities. We can measure these densities today and calculate how they evolved backward in time. This gives us a redshift to age conversion. A galaxy at redshift 10 existed about 450 million years after the Big Bang. Gupta's model challenges this interpretation by adding a tired light component. If some of the redshift comes from photons losing energy rather than space expansion, distant galaxies aren't as far or as young as standard conversions suggest. A galaxy we measure at redshift 10 might actually be at effective redshift 7 if we account for energy loss effects. That would place it closer and later in cosmic history, giving it more time to form stars and build mass. The hybrid model essentially recalibrates the cosmic distance ladder and the timeline attached to it. The implications are profound. Redshift is cosmology's ruler. Almost everything we know about the distant universe comes from interpreting redshift. Galaxy formation timelines. The history of star formation across cosmic time, when the first black holes formed, when elements were created, all depend on converting redshift measurements to ages. If that conversion is wrong, every timeline in cosmology needs revision. The entire history of the universe gets rewritten. Events we thought happened 500 million years after the Big Bang might have happened 1 billion years later. The cosmic dawn we've been studying wasn't the dawn at all, just early morning. Testing which interpretation is correct requires multiple independent measurements. One powerful check involves Type 1a supernovae. These exploding stars have consistent intrinsic brightness, making them excellent standard candles for measuring distances. By observing supernovae at various redshifts, astronomers trace cosmic expansion history directly. The supernova data strongly supports standard expansion, with no tired light component. This was one of the original reasons tired light was rejected. Gupta argues his hybrid model can match supernova data because the expansion component dominates over the small, tired light correction for the distances where supernovae are observable. Another test involves gravitational lensing. Massive galaxies and galaxy clusters bend light from more distant objects behind them. The amount of bending depends on the mass of the lens and the geometry of space between us, the lens, and the background object. That geometry depends on redshift and expansion history. Thousands of gravitational lenses have been observed. They all match predictions from standard expansion cosmology remarkably well. Adding a tired light component would change lensing predictions slightly. So far, no discrepancy has been detected, but the measurements aren't yet precise enough to rule out small tired light contributions. The cosmic microwave background provides the most powerful constraint. This radiation shows us the universe at redshift around 1000, when it was 380,000 years old. The CMB's temperature, uniformity, and detailed pattern of fluctuations are exquisitely explained by standard expansion cosmology. Any modification to how redshift relates to cosmic time must still reproduce CMB observations perfectly. Gupta's model attempts this by keeping the expansion component dominant and adding evolving coupling constants to maintain consistency. Whether this actually works requires detailed calculations that are still being debated. What's becoming clear is that redshift, our most fundamental cosmological tool, might be more complicated than we thought. It might not be a pure measure of space expansion. There could be additional effects we've been ignoring, either because they're small and hard to detect or because we weren't looking for them. If the James Webb discoveries force us to reconsider the universe's age, redshift interpretation must be part of that reconsideration. The galaxies aren't lying about their properties. They really are massive and mature. Either they formed impossibly fast under exotic physics, or our method for determining when they formed is systematically biased. The second option is simpler, but it requires admitting that cosmology's most trusted measurement technique might need a correction. In the late 1990s, two teams of astronomers made a discovery that won them the Nobel Prize and upended cosmology. They were studying Type 1a supernovae, stellar explosions that shine with consistent brightness across the universe. By measuring how dim these supernovae appeared at various distances, the teams expected to determine whether cosmic expansion was slowing down. Instead, they found something shocking. Distant supernovae were dimmer than expected. The universe's expansion wasn't slowing, it was accelerating. This led to the discovery of dark energy and refined estimates of the universe's age to 13.8 billion years. That same supernova data now poses problems for standard cosmology. The issue isn't the acceleration. That's been confirmed by multiple independent observations. The problem is the exact rate of acceleration and what it implies about the Hubble constant, the number describing how fast space expands. Different methods for measuring the Hubble constant give different answers. Nearby supernovae and distant ones don't quite agree. This disagreement suggests either our measurements have systematic errors or our cosmological model is incomplete. The tension has grown worse as measurements improved. One group of researchers uses supernovae, pulsating stars called Cepheids, and other local distance indicators to measure the current expansion rate. They consistently get values around 73 kilometers per second per megaparsec. This means a galaxy 1 megaparsec away, about 3 million light years, recedes at 73 kilometers per second due to space expansion. That measurement implies the universe is younger than 13.8 billion years. Depending on exact assumptions, it suggests ages between 12.5 and 13 billion years. This conflicts with cosmic microwave background measurements. The cosmic microwave background tells a different story. The Planck satellite mapped the CMB with incredible precision, measuring tiny temperature variations across the sky. These variations encode information about the universe's composition, geometry, and expansion history. By fitting theoretical models to Planck data, cosmologists derive a Hubble constant around 67 kilometers per second per megaparsec. That lower value implies a slower expansion rate and an older universe, around 13.8 billion years. The two measurements disagree by nearly 10%. That might not sound like much, but in cosmology, it's huge. This disagreement is called the Hubble tension, and it's become one of the field's most pressing problems. Scientists have checked for systematic errors repeatedly. Distances might be miscalibrated. Supernova properties might vary in ways we don't understand. Cosmic microwave background analysis might have subtle issues, but years of scrutiny haven't resolved the tension. Both measurements appear robust. If anything, as techniques improve, the disagreement becomes more statistically significant. Either something is systematically wrong with one method, or there's new physics operating that standard cosmology doesn't capture. Some researchers proposed exotic solutions. Maybe dark energy evolves over time rather than remaining constant. Perhaps there's an additional component of radiation or matter in the early universe that affects the CMB, but not local measurements. Others suggested modifications to general relativity itself, altering how gravity operates on cosmic scales. These ideas are creative but speculative. They add complexity to the model without clear physical motivation beyond fixing the tension. Most cosmologists hoped for a simpler explanation. Some overlooked error in measurements that would make the tension disappear. Gupta's older universe model offers another perspective. If the universe is actually 26.7 billion years old, the entire framework for interpreting both supernova data and CMB observations shifts. The conversion from redshift to time changes. The relationship between expansion rate and age changes. While Gupta's model doesn't resolve the Hubble tension directly, it suggests the tension might be a symptom of using the wrong cosmic timeline. When you assume the universe is 13.8 billion years old and force observations into that framework, contradictions appear. Expand the timeline, and there's more room for expansion rate to vary in ways that reconcile different measurements. However, this solution creates its own difficulties. Supernova cosmology is precision science. The 1990s discoveries were replicated and extended by observing hundreds of supernovae at various distances. The entire body of data fits standard expansion cosmology well. Adding a tired light component, as Gupta does, changes how we interpret supernova distances and brightnesses. The tired light contribution must be carefully calibrated to match observations without destroying the excellent fit that standard cosmology already achieves. Critics argue this fine-tuning is suspicious. It feels like adjusting the model to get the desired answer rather than letting data dictate the conclusion. Moreover, recent supernova observations from James Webb complicate the picture further. Webb can observe supernovae at higher redshifts than ever before, probing the universe when it was younger. Early results show these distant supernovae behave as standard expansion predicts, with no obvious anomalies suggesting tired light effect. If tired light operated, we might expect to see deviations at extreme distances where the effect accumulates most. So far, nothing has been detected. This doesn't rule out a small tired light component, but it constrains how large the effect can be. The supernova evidence crisis is really two crises. First, the Hubble tension showing that local and distant universe measurements disagree. Second, the challenge of incorporating any modifications like tired light without breaking the successful fit to existing data. Both crises suggest standard cosmology is missing something. Whether that something is a longer cosmic timeline, evolving dark energy, new physics, or systematic measurement errors remains unclear. What's certain is that supernovae, those brilliant stellar deaths, are telling us something important about the universe's true age and history. We just haven't fully deciphered their message yet. Orbiting the Milky Way are ancient relics from the galaxy's youth. Globular clusters, dense spheres containing up to 1 million stars each, float in the galactic halo like cosmic fossils. These clusters are special. All their stars formed around the same time from the same gas cloud. They're time capsules, preserving information about conditions when the galaxy was young. By studying globular cluster stars, astronomers can measure how old the Milky Way is. The results have always been uncomfortable. The clusters appear nearly as old as the universe itself, leaving almost no time between the Big Bang and their formation. Measuring a globular cluster's age requires understanding stellar evolution in detail. Stars in these clusters span a range of masses. The most massive stars burned through their fuel quickly and died billions of years ago. What remains are low-mass stars still burning hydrogen, medium-mass stars that have evolved off the main sequence, and stellar remnants like white dwarfs. By plotting the cluster's stars on a diagram showing their brightness versus color, astronomers create a pattern that reveals the cluster's age. The exact shape of this pattern depends on when the stars formed and how they've evolved since. The oldest globular clusters in the Milky Way show ages around 12 to 13 billion years. Some estimates push to 13.5 billion. These measurements come with uncertainties of several 100 million years, but the central values are consistently very old. Given that the universe is supposedly 13.8 billion years old, this leaves only 300 million years for the Big Bang to occur, the universe to cool enough for atoms to form, the first stars to ignite, those first stars to die and enrich space with metals, and globular clusters to coalesce from that enriched material. The timeline is crushingly tight. Astronomers tried various adjustments to make globular cluster ages fit more comfortably. Maybe stellar evolution models are wrong. Perhaps the mixing of elements inside stars occurs faster than we think, making old stars appear older than they are. Maybe distances to globular clusters have systematic errors, affecting brightness measurements and age estimates. These adjustments can reduce estimated ages by several 100 million years, but they require pushing stellar physics in directions that create problems elsewhere. The most natural interpretation of globular cluster observations continues to suggest ages that nearly match or exceed the universe's supposed age. In 2024, a team of researchers published a new approach to dating globular clusters. Instead of relying solely on stellar evolution models, they studied blue straggler stars. These strange objects appear younger and bluer than other stars in ancient clusters. They're thought to form through stellar collisions or mass transfer between binary stars. The number and properties of blue stragglers in a cluster provide an independent age estimate. Applying this method to several clusters yielded results that troubled cosmologists. The ages came out consistent with a universe significantly older than 13.8 billion years. The team explicitly stated their findings support the idea that the universe may be older than standard models indicate. They pointed to Gupta's work on the 26.7 billion year universe as offering a framework that could accommodate their measurements. This independent confirmation from a completely different technique strengthened the case that something is wrong with the standard cosmic timeline. It's one thing when telescope observations of distant galaxies create problems. It's another when stars in our own galaxy's backyard tell the same story. Globular clusters exist around other galaxies too. The Andromeda Galaxy has its own population. Distant galaxies photographed by Hubble and Webb show what appear to be globular clusters forming in the early universe. These ancient cluster populations across cosmic history provide a consistency check. If our Milky Way clusters are genuinely as old as they appear, clusters in other galaxies should show similar ages. And they do. Everywhere we look, globular clusters push uncomfortably close to the universe's supposed age. Either every galaxy in the cosmos formed its globular clusters in a brief window right after the Big Bang, or that window wasn't as brief as we think. The alternative explanation is simpler. If the universe is 26.7 billion years old, globular clusters with ages around 13 or 14 billion years aren't problematic. They formed roughly halfway through cosmic history, giving plenty of time for the Big Bang, the first stars, metal enrichment, and cluster formation. The Milky Way itself would have more time to assemble through mergers of smaller galaxies. The ancient ages that seem impossible in a 13.8 billion year timeline become perfectly reasonable in a doubled timeline. No exotic stellar physics needed, no systematic errors required, just more time. Critics point out that extending the universe's age creates different problems. If globular clusters formed 13 billion years ago in a 26.7 billion year old universe, what was happening for the first 13 billion years? Why did cluster formation wait so long? Supporters argue this actually makes sense. The very first generation of stars contained zero metals. They couldn't form planets or complex structures. When they exploded, they enriched space with heavy elements for the first time. The second generation of stars and clusters needed that enrichment. Perhaps cluster formation required waiting for sufficient metal buildup, which took billions of years. An older universe provides time for this gradual enrichment process. The debate over globular cluster ages highlights a broader issue in cosmology. We have multiple independent ways to measure cosmic time: expansion rate observations, cosmic microwave background analysis, stellar evolution models, radioactive dating of meteorites. All these clocks should agree. When they don't, something is wrong. Globular clusters represent one of the oldest clocks available. They're telling us they formed 13 billion years ago or more. Either we adjust our understanding of stellar physics to make them younger, or we adjust our understanding of cosmic history to give them more time to exist. The second option is looking increasingly necessary. 380,000 years after the Big Bang, something extraordinary happened. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, space was opaque, filled with a plasma of charged particles that scattered light in every direction. After atoms formed, photons could travel freely for the first time. The light from this era has been traveling through space ever since, stretched by cosmic expansion into microwaves. This cosmic microwave background, discovered in 1964, is the oldest light we can see. It's also the strongest evidence for the Big Bang theory and the primary basis for calculating the universe's age. The CMB appears incredibly uniform. Look in any direction in space, and you'll see microwave radiation at the same temperature, around 2.7 Kelvin above absolute zero. This uniformity presents a puzzle. Regions of the universe separated by vast distances, which shouldn't have had time to exchange energy and equalize temperature, somehow have identical temperatures. Standard Big Bang theory struggled to explain this. The solution came from inflation theory, proposed in the early 1980s. Inflation suggests a brief period of exponential expansion in the universe's first fraction of a second stretched a tiny, uniform patch to cosmic scales. Within the uniformity are tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations are crucial. They represent slight density differences in the early universe. Denser regions had slightly more gravity, attracting more matter. Over time, these density seeds grew into galaxy clusters and cosmic structure. The pattern of fluctuations in the CMB encodes information about the universe's composition, age, and geometry. By measuring these patterns precisely, cosmologists can determine fundamental properties of the cosmos. The Planck satellite, operated by the European Space Agency, mapped the CMB with exquisite detail from 2009 to 2013. The resulting data fits standard cosmology beautifully. The Lambda CDM model, incorporating dark matter, dark energy, and normal matter in specific proportions, matches Planck observations to extraordinary precision. From this fit, cosmologists derive the universe's age, 13.797 billion years, plus or minus 23 million years. Less than 1% uncertainty. The CMB seemed to have closed the book on cosmic age debates. But the CMB carries assumptions built into its interpretation. The conversion from CMB observations to cosmic age depends on models of how the universe expanded and cooled. Standard analysis assumes expansion follows general relativity with dark energy and dark matter. It assumes the physics of light and matter interactions remained constant throughout history. Change these assumptions, and the derived age changes too. Gupta's model, incorporating evolving coupling constants, challenges these assumptions. If the constants governing photon interactions were different when the CMB formed, we're misinterpreting the data. Specifically, the CMB's temperature and fluctuation pattern depend on physical processes during recombination when atoms formed. The rate at which electrons and protons combined, the opacity of the plasma before recombination, the propagation speed of sound waves in the primordial gas, all depend on fundamental constants. If those constants evolved as Gupta suggests, the processes occurred differently. What looks like a universe 13.8 billion years old under constant constants might actually be a universe 26 billion years old with evolving constants. The same observations could fit either scenario with appropriate parameter adjustments. This creates a problem. The CMB is often called cosmology's gold standard, the observation that most tightly constrains models. If the CMB can be interpreted in multiple ways depending on assumptions about evolving constants, its constraining power weakens. Critics of Gupta's model emphasize this issue. They argue that adding free parameters like time-varying constants allows fitting almost any data. The model becomes unfalsifiable, capable of explaining anything, and therefore explaining nothing. For an older universe model to be taken seriously, it must predict specific, testable differences in the CMB pattern that standard cosmology doesn't predict. One potential test involves the scale of CMB fluctuations. Inflation theory predicts that fluctuations should appear on scales larger than the cosmic horizon at recombination time. These super-horizon fluctuations are a key signature that inflation occurred before the Big Bang. Standard cosmology sees these clearly in CMB data. If the universe is twice as old, the horizon scale calculation changes. Super-horizon fluctuations might appear at different angular scales on the sky. Future CMB experiments with higher resolution could potentially distinguish between standard and extended timeline models by precisely measuring these scales. Another CMB mystery involves subtle anomalies that don't fit the Lambda CDM model perfectly. There's a cold spot, a region with lower than expected temperature. The distribution of fluctuations on large angular scales shows slight deviations from predictions. These anomalies are at low statistical significance, possibly just random fluctuations, but they've persisted through multiple analysis methods. Some cosmologists wondered if they hint at new physics. An older universe with different early expansion history might naturally explain these anomalies, or they might be nothing. The data isn't conclusive either way. What is clear is that the CMB remains the most important constraint on any alternative cosmology. You can't propose a new model without showing it reproduces CMB observations. Gupta's work attempts this by carefully balancing the tired light component, evolving constants, and standard expansion to maintain agreement with Planck data. Whether this succeeds requires expert analysis beyond simple claims. Multiple research groups are currently studying whether Gupta's approach genuinely fits all CMB observations, or whether hidden inconsistencies exist. The CMB has demolished many alternative cosmologies. It might demolish the older universe idea too, or it might, with more careful analysis, become evidence for it. The mystery isn't solved yet. 85% of the universe's matter is invisible. It doesn't emit light. It doesn't absorb light. It interacts only through gravity. We call it dark matter, and we know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than all their stars and gas combined. Gravitational lensing bends light in ways that require additional unseen mass. Dark matter permeates the universe, and its gravity shaped every structure we see. Understanding galaxy formation means understanding dark matter, and that's where the timeline problems become acute. In standard cosmology, dark matter clumped together first. Right after the Big Bang, tiny quantum fluctuations in dark matter density got amplified by cosmic expansion. Denser regions had stronger gravity, pulling in more dark matter. Over millions of years, these density peaks grew into massive halos. Regular matter, hydrogen, and helium gas fell into these dark matter wells. The gas cooled, fragmented, and formed the first stars and galaxies. This process is hierarchical. Small structures form first. They merge into larger structures over time. The Milky Way built up through hundreds of mergers of smaller galaxies across billions of years. The key word is time. Hierarchical structure formation is slow. Dark matter halos grow gradually. Mergers take hundreds of millions of years to complete. Gas cooling and star formation have their own timescales. In simulations, starting from a 13.8 billion-year-old Big Bang, the first galaxies don't appear until around 200 million years later. They're small, containing perhaps 10 million stars. By 500 million years after the Big Bang, you might have galaxies with 100 million stars if everything goes perfectly. Structures as large as the Milky Way take 10 billion years or more to assemble. James Webb found massive galaxies at 500 million years containing billions of stars. This breaks the hierarchical timeline. Either structure formation was radically accelerated in the early universe, or the universe had more time than the standard model allows. Acceleration is hard to explain with known physics. Dark matter interactions are weak. You can't make dark matter clump faster without changing fundamental properties. Some theorists proposed that dark matter in the early universe was warmer or more interactive, allowing faster clumping. But these modifications create problems matching other observations like the cosmic microwave background pattern. Another challenge involves feedback processes. When stars form in dark matter halos, they don't just quietly accumulate. Massive stars explode as supernovae. The explosions heat gas and blow it out of the halo. This prevents further star formation temporarily. The halo needs time to cool down and attract more gas before making more stars. Feedback limits how fast galaxies can grow. It's an essential part of galaxy formation physics, preventing runaway star formation from creating structures far larger than observed. But early massive galaxies seem to have ignored these limits. Some researchers suggested dark matter halos in the early universe were unusually dense. Denser halos have stronger gravity, holding onto gas even when supernovae try to blow it away. This might allow higher star formation efficiency. Simulations showed this works to some extent, creating somewhat more massive galaxies than standard models predict. But the effect isn't strong enough to produce Milky Way-sized galaxies in under 1 billion years. The early massive galaxies remain unexplained unless you invoke truly exotic dark matter physics that has no other supporting evidence. An older universe resolves this naturally. If cosmic dawn occurred 2 billion years after the beginning instead of 500 million, dark matter halos had 3 to 4 times longer to grow. Hierarchical formation proceeds at its normal, slow pace. Mergers happen gradually. Feedback operates as expected. By the time we observe these galaxies through James Webb, they've had sufficient time to reach their observed masses through conventional physics. No exotic dark matter properties needed. No accelerated formation mechanisms required. Just standard structure formation with more time to work. There's another consideration. Dark matter dominated the universe's early evolution. Regular matter was initially too hot and turbulent to clump efficiently. Dark matter, being cold and non-interacting, could clump immediately. The first dark matter halos formed perhaps 50 to 100 million years after the Big Bang. But these halos were tiny, with masses equivalent to 1 million solar masses. Growing them to sizes capable of hosting massive galaxies takes time. The merger tree, the genealogy of how small halos merge into large ones, has minimum timescales determined by orbital dynamics and gravitational interaction rates. You can't rush it. Current simulations of structure formation in the standard 13.8 billion year timeline produce the galaxy distribution we observe today quite well, but they struggle with the early universe. Webb observations show more massive galaxies at high redshift than simulations predict. Researchers have tried adjusting simulation parameters, star formation efficiency, feedback strengths, and dark matter properties. They can reduce the discrepancy but not eliminate it. The simplest fix remains giving the simulations more time by extending the cosmic timeline. Then the early massive galaxies appear naturally without parameter tuning. Dark matter's role in all this is secure. No one doubts dark matter exists, or that it drives structure formation. The question is whether structure formation in a 13.8 billion year timeline can produce what we observe. The evidence increasingly suggests it cannot. Dark matter works perfectly fine. It just needs more time to build the massive structures James Webb found. An older universe provides that time. It lets dark matter do its job without requiring exotic modifications to its properties or invoking special conditions in the early universe. The physics stays simple. The timeline gets longer, and suddenly, everything dark matter built makes sense. When the universe began, it contained exactly 3 elements: hydrogen, helium, and trace amounts of lithium. That's it. No carbon, no oxygen, no iron, no gold. Everything heavier than lithium had to be created inside stars through nuclear fusion and scattered across space by stellar explosions. This means the oldest stars should be almost pure hydrogen and helium, while younger stars gradually become richer in heavy elements. Astronomers measure this through metallicity, the fraction of a star's mass in elements heavier than helium. Studying metal, poor stars, lets us probe the early universe directly. Population 3 stars, the very first generation, should have 0 metallicity. They formed from primordial gas, untouched by previous stellar explosions. Theory predicts these stars were massive, hundreds of times our own star's mass, shining intensely blue and dying within a few million years. Their supernovae seeded space with the first heavy elements. But we've never seen a population 3 star. Every star observed has some metal content, suggesting they formed after the first generation ended. The absence of 0 metallicity stars makes sense if they all died quickly, but it also means we can't directly observe the very first epoch of star formation. Population 2 stars formed next. These stars, like Methuselah, have very low metallicity, around 100th to 1000th the metal content of our own star. They're ancient, forming within the first billion or so years of cosmic history. Our galaxy's halo and globular clusters contain many population 2 stars, preserved from the Milky Way's youth. By studying them, we learn about conditions when the galaxy assembled. Population 1 stars, including our own star, formed later from gas enriched by multiple generations of supernovae. They have relatively high metallicity, containing percent-level abundances of heavy elements. The distribution of metallicity among stars tells a story of chemical enrichment over time. In a 13.8 billion year timeline, population 2 stars had to form extremely early, within maybe 500 million to 1 billion years after the Big Bang. This requires rapid formation and death of population. 3 stars, quick enrichment of gas to population 2 metallicity levels, and immediate formation of long-lived population 2 stars before much further enrichment occurred. The timeline is tight. Every process needs to happen efficiently and quickly with no delays. Observations complicate this picture. Some population 2 stars show chemical abundance patterns that don't match simple models. They have odd ratios of different elements, suggesting complex enrichment histories. The first supernovae should have produced specific element ratios determined by fusion physics, but observed ratios sometimes deviate. This suggests metal-poor stars formed from gas enriched by multiple supernovae with different properties, implying a longer, more complex enrichment process than the tight timeline allows. An older universe provides breathing room for this complexity. Another puzzle involves the most metal-poor stars discovered. A few stars have been found with metallicity 100,000th that of our star. These objects formed from gas enriched by perhaps just 1 or 2 supernovae. They represent the closest we've come to observing population. 2.5 stars, intermediate between the first and second generations. Their existence and properties constrain models of the first supernovae. Current models barely fit the observations within the standard timeline. Extending the timeline would allow more time for diverse first supernovae to occur and create the range of metal-poor stars we observe. The metal enrichment history of the universe follows a specific trajectory. Start with 0 metals at the Big Bang. First stars form, live briefly, explode. Metallicity jumps from 0 to maybe 1/10,000th its current value. More stars form from enriched gas, live, die. Metallicity gradually climbs. By the time our star formed 4.6 billion years ago, metallicity had reached roughly its current level. The slope of this enrichment curve depends on star formation rate and supernova frequency. In simulations, matching the observed curve requires careful tuning of parameters in a 13.8 billion year timeline. An older timeline flattens the curve, making the required star formation rate and supernova frequency more reasonable. Globular clusters provide snapshots of metal enrichment at specific early times. All stars in a cluster formed from the same gas cloud and have nearly identical metallicity. By measuring multiple clusters' metallicities and ages, astronomers trace the enrichment history. The pattern shows rapid early enrichment, then slower enrichment as the galaxy matured. This rapid early phase suggests intense star formation and frequent supernovae in the young Milky Way. But rapid also means efficient. Every supernova's worth of metals gets incorporated into new stars quickly. The timeline barely allows for this efficiency. A longer timeline permits a less frantic, more physically plausible enrichment process. Recent discoveries of high redshift galaxies by James Webb include spectroscopic measurements of their metallicity. Some early galaxies already show substantial metal enrichment, reaching 1/10 the metal content of our star just 500 million years after the Big Bang in the standard timeline. Creating that much metal that quickly requires multiple generations of stars forming and exploding within a few hundred million years. Each generation takes tens of millions of years. The math is strained. If those galaxies actually existed 1 or 2 billion years after the beginning, the enrichment timeline relaxes. Multiple generations have time to occur without invoking unrealistic efficiency. The metal-poor star population is telling us something fundamental about the early universe's pace. Chemical enrichment, star formation, and stellar evolution all have inherent timescales determined by physics. You can't arbitrarily speed them up. Fusion reactions proceed at rates set by nuclear cross-sections. Stellar lifetimes depend on mass and fusion rate. Supernova ejecta expand at velocities determined by explosion energy. These aren't adjustable parameters. They're fixed by the laws of physics. If observations require more enrichment, more generations, more evolution than the timescales allow, the only solution is extending the time available. An older universe does exactly that. For decades, cosmologists spoke of the Big Bang as the absolute beginning. Time itself started in that fireball 13.8 billion years ago. Asking what came before was meaningless, like asking what's north of the North Pole. But in the early 1980s, physicist Alan Guth proposed something radical. What if the Big Bang wasn't the beginning? What if something came before? A period of exponential expansion called cosmic inflation. This idea transformed cosmology and opened the door to thinking about pre-Big Bang time. Inflation solves several problems that plagued Big Bang theory. The horizon problem? Distant regions of the universe have identical temperatures despite never having been in contact to equalize. The flatness problem. The universe's geometry is almost perfectly flat, requiring fine-tuned initial conditions. The monopole problem. Theories predicted exotic magnetic monopole particles should be common, but we never find them. Standard Big Bang offers no explanation for these puzzles. Inflation explains them all elegantly by proposing a brief period of faster-than-light expansion in the universe's first fraction of a second. Here's how it works. Imagine the universe at 10 to the negative 36 seconds after time began. It's unimaginably small, maybe the size of a proton, but it's already smooth and uniform because it's so tiny that light has had time to travel across it. Suddenly, a strange form of energy permeating empty space itself, called the inflaton field, drives exponential expansion. The universe doubles in size repeatedly, at least 80 times in less than a trillionth of a second. This expansion is so fast that it dwarfs the speed of light. But that's okay because space itself expands. Nothing moves through space faster than light, but space can grow arbitrarily fast. After inflation ends, the inflaton field's energy converts into particles and radiation. This conversion floods space with matter and energy, creating the hot, dense conditions of the Big Bang. Everything we call the Big Bang, the hot plasma state, the formation of elements, the cooling and expansion, all of that happens after inflation stops. Inflation precedes the Big Bang, making the Big Bang not a beginning but a transition from one state to another. This completely changes the conceptual framework. Time extends before the hot Big Bang to the inflationary era. The implications are staggering. If inflation happened, the observable universe is just a tiny patch of a vastly larger space. During inflation, our patch was stretched to cosmic scale, but other patches underwent the same process. The total space might be infinite, filled with countless regions like ours, each experiencing its own Big Bang when inflation ended locally. This leads to the multiverse concept. Our universe is one bubble in an eternal sea of inflating space, with new bubble universes constantly forming. We can never see beyond our cosmic horizon, but theoretically, other universes exist out there. Evidence for inflation comes from the cosmic microwave background. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the density variations we see as temperature fluctuations in the CMB. The pattern of these fluctuations matches inflation predictions remarkably well. Inflation also predicts a nearly flat universe geometry, which observations confirm. and it predicts a specific type of fluctuation spectrum, nearly scale invariant, which is exactly what we observe. No alternative theory explains all these observations as simply as inflation does. But inflation creates its own mysteries. What is the inflaton field? Where did it come from? What caused inflation to start and stop? These questions remain unanswered. Various models propose different inflaton physics, but we lack direct evidence distinguishing between them. The one thing most models agree on is that inflation requires a state before the hot Big Bang. That pre-Big Bang state, cold and empty except for the inflaton field energy, existed for some duration. How long? That depends on when inflation started, which we don't know. Gupta's older universe model fits naturally with inflation. Standard cosmology already accepts that time extends before the hot Big Bang to the inflationary era. Gupta just extends it further. If the hot Big Bang happened 13 billion years ago instead of 13.8 billion, and inflation preceded that by some amount, the total age becomes longer. But there's a deeper connection. Inflation theory shows that asking about pre-Big Bang time is legitimate. Time didn't necessarily begin at the hot Big Bang. It might stretch back through inflation and beyond to whatever caused inflation to start. Some cosmologists go further, proposing eternal inflation. In this scenario, inflation never completely ends everywhere. Locally, in regions like ours, inflation stops and a Big Bang occurs. But in other regions, inflation continues forever, constantly creating new space. This process has no beginning or end. It's eternal to the past and future. Our hot Big Bang becomes just one event in an infinite timeline of inflation-generating bubble universes. If eternal inflation is correct, the age of our universe is finite, but the age of the larger structure containing us is infinite. Recent observations from James Webb provide indirect tests of inflation. The mature early galaxies could constrain models of what happened during and after inflation. If structure formation started earlier than standard models predict, it might tell us something about the transition from inflation to hot Big Bang. Different inflation models predict slightly different outcomes for how quickly structure forms afterward. The galaxy observations don't yet discriminate between models definitively, but they're beginning to provide useful constraints. What's clear is that inflation changed how cosmologists think about beginnings. The Big Bang isn't the start of time. It's an event following inflation, and inflation might follow something else. The chain of causation extends backward beyond what we can currently observe. This philosophical shift makes proposals like Gupta's older universe more palatable. If we already accept time before the Big Bang through inflation, accepting even more pre-Big Bang time is a smaller conceptual leap. The universe's history is longer and more complex than a simple explosion 13.8 billion years ago. How much longer? That's what observations and theories are beginning to tell us. If the universe is older than we thought, the implications ripple far beyond fixing galaxy formation timelines. An extended cosmic history connects to one of the most controversial ideas in modern physics, the multiverse. The concept that our universe is just one among countless others isn't science fiction. It emerges naturally from several well-developed theories, including eternal inflation, and an older universe fits more comfortably into multiverse frameworks than a younger one does. The connection isn't obvious at first, but it's profound and unavoidable once you see it. Eternal inflation, mentioned earlier, proposes that inflationary expansion never fully ends. It stops locally in patches like ours, creating bubble universes with their own hot Big Bangs. But between the bubbles, space continues inflating exponentially, constantly generating more volume that spawns more bubbles. This process has no end and, according to some models, no beginning. It's been happening eternally. Our observable universe is one bubble in an infinite cosmic foam. Other bubbles exist beyond our horizon, forever out of reach because space between us and them expands faster than light travels. Each bubble universe might have different physical properties. The strength of fundamental forces, the masses of particles, even the number of spatial dimensions could vary from bubble to bubble. These properties are determined by how the inflaton field decays when inflation ends locally. Random quantum fluctuations during inflation could set different physical constants in different bubbles. Most bubbles would be lifeless, with physics incompatible with structure formation. We find ourselves in a rare bubble where constants permit galaxies, stars, and life. This anthropic reasoning explains why our universe seems fine-tuned. It's not fine-tuned. It's randomly selected from infinite possibilities, and we exist in one where existence is possible. The multiverse isn't just speculation. String theory, a leading candidate for unifying physics, predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws. The number of possibilities is enormous, perhaps 10 to the 500th power or more. Each bubble universe in eternal inflation could realize a different vacuum state from the landscape. This connects quantum gravity to cosmology in a deep way. The multiverse becomes the natural setting for string theory to operate in. Single universe models start looking special and unlikely. An older universe changes the multiverse picture in subtle but important ways. If our bubble formed 13 billion years ago, rather than 13.8 billion, our position in the eternal inflation process shifts. We're slightly older relative to other bubbles. The statistical distribution of bubble ages throughout the multiverse depends on details of how inflation proceeds. If some mechanism favors longer-lasting inflation before bubbles nucleate, the typical bubble might be older than standard models predict. Our bubble's age would reflect this. Finding that we're older than expected might be evidence for specific inflation models over others. There's also a connection to the measure problem in eternal inflation. This technical issue asks how to calculate probabilities in an infinite multiverse. If infinitely many bubbles exist, and infinitely many contain observers like us, how do we determine what's typical versus rare? Different approaches to this problem, called measures, predict different age distributions for observer-bearing bubbles. Observational data about our universe's age, formation history, and properties constrain which measures work. An older universe might favor certain measures over others, helping narrow down theories. Another multiverse variant comes from quantum mechanics. The many worlds interpretation suggests that every quantum measurement spawns parallel branches of reality, each corresponding to a different outcome. This creates an unfathomably vast multiverse of quantum branches, far more numerous than eternal inflation bubbles. Our universe's history is just one pathway through this quantum multiverse. An older universe means our pathway is longer, with more branch points in the past. The implications for quantum probability and the nature of time become increasingly complex as the timeline extends. Cyclic universe models provide yet another multiverse flavor. These models propose that Big Bangs and Big Crunches repeat in cycles. Our Big Bang was preceded by a previous universe that contracted and bounced. That previous universe might have been preceded by another, extending infinitely into the past. Each cycle might be slightly different, with different physical constants or initial conditions. We inhabit one cycle in an eternal sequence. If the cycle duration is around 26 billion years, matching Gupta's age estimate, our current cycle is roughly halfway through before eventual contraction begins. Not everyone accepts the multiverse. Critics argue it's untestable, and therefore not science. If other universes are forever beyond observation, how can we ever prove they exist? Defenders respond that many accepted scientific theories involve unobservable entities. Electrons can't be directly seen. The interior of black holes is hidden from view. We infer their existence from observable effects. Similarly, we might infer the multiverse from observations like the universe's age, the values of constants, and the properties of the cosmic microwave background. The multiverse makes predictions about what we should observe in our bubble. An older universe strengthens some multiverse models and weakens others. Models that predict young bubble universes struggle if ours is actually old. Models that allow wide age variation accommodate the finding easily. As observations from James Webb and other instruments refine our knowledge of cosmic history, they're not just telling us about our universe. They're constraining theories about the much larger multiverse structure our universe might inhabit. The age of everything is becoming a clue to whether everything extends far beyond what we can see. The philosophical implications are dizzying. If we're one bubble among infinite bubbles, our significance seems diminished. But it also means existence is more abundant than we imagined. Life and consciousness might arise in countless bubbles, making the cosmos far richer than a single universe could ever be. An older timeline in our bubble doesn't change the multiverse's vastness, but it does change our understanding of where we sit within it. We're not in a freshly nucleated young bubble, we're in a mature bubble that's had more than twice the time we thought to develop its complexity. That's humbling and awe-inspiring simultaneously, revealing just how much we still don't know about the full extent of reality.